And so these end user networks here need to be able to support this increasing demand as well as the access networks as well. Now, before we deep dive into the access network, let's talk about the telecoms network, whereby horizontally, and this is very high level, we can actually separate this network into four segments: the core, the metro, the access, as well as the end user networks. Now, the core network is a mesh of routers and switches, whereby it can provide connectivity as well as routing, between all parts of the network. We have metro network after that, whereby, as the name suggests, it actually aggregates and distributes that traffic. Then we have the access network, which provides direct connection to these end user networks here, whereby it can actually come as a part of a fiber wireless. So actually, fiber mobile convergence here, as well as a fully fiber. I'm just wondering whether I'm stepping on something.
No.
A fully fiber.
Sometimes if you lower the resolution, it helps.
We'll probably do it for the next. Okay. All right. So then here, as you look at the fully fiber direct connectivity, we have fiber to the X. And it's typically in a passive optical architecture, which means point to multi-point. And this particular architecture has many benefits. For example, low cost, scalable, low real estate, example here at the optical line terminal, as well as low energy footprint. So these are the benefits. And in some parts of the world, we have other alternatives such as cable modem as well as DSL. Now here I want to look at the global market share of broadband access, whereby you'll notice two things. The first thing is that FTTX with the PON is actually quite lumpy across the geographical region, so the market share is not the same, and this predominantly is based on, it's due to legacy systems. For example, in Western Europe, we have DSL. But however, over the course of the next, 5 to 10 years, we're expecting FTTX to gain market share, especially when these legacy systems are being sunsetted and decommissioned. And so shown here, we have global PON equivalent revenue. As you can see here, it's supposed to forecast, it is forecast to reach 20 billion in 2028. So, PON is no longer an emerging market, it is an established market. And, this forecast is based on the fact that, as I've said, legacy systems are being replaced, operators are now actually replacing first generation PON. PON technology is also finding new applications in new markets. And so the question is, what are these new markets? And so it's, no surprise that, with the number of connected devices per home, number of connected devices per user per home in the future, amounting to about 15 per person, you will see that, fiber is now encroaching from the distribution network into the building, into the home, into the room. And shown here is an architecture by ITUT that talks about use cases and requirements of fiber to the room. And here you can see FTT are providing in-home connectivity to support next generation Wi-Fi access points in each room. And, with Wi-Fi 7, with a theoretical capacity, of up to 46 gigabits per second, we need a technology that doesn't serve as a bottleneck. We need a technology that provides seamless connection with comparative bit rates. And so the fiber to the home technology, such as the PON, is a natural choice to meet capacity and reliability requirements. Similarly, PON is also, already in certain parts of our country anyway, deployed in enterprise offices. So these are private offices and campuses. And so organizations may choose to build and maintain private networks with dedicated edge data centers. And so here, the technology provides dedicated, private, secure, high capacity, and it actually delivers a range of services as well as sharing of computer resources. And so aside from residential and business use cases, we also find PON as an emerging use case in manufacturing, whereby, it provides broadband connectivity to allow deterministic networking of smart automation and manufacturing in Industry 4.0, as well as latency-sensitive collaborative interactions, which you'll see as part of this presentation later on between humans and robots in the industrial environment. So this one is quite interesting. PON is actually also finding use cases for smart grid communications. So when it comes to smart grid that uses renewable resources, the stabilization of this grid requires really comprehensive management of load and storage control between the grid elements to actually load as well as store this renewable energy. And so PON is a natural selection or natural choice for this, whereby the optical line terminal can be actually built into the substation, whereby it monitors and communicates load and storage control information. And then the optical network unit can be built into grid elements such as switching stations, pole-mounted switches, and main units. And so fiber really is a great solution. It is low cost, it is tolerant to extreme conditions and environments. It is safe, can be made safe, as well as secure with transmission protocols and higher layer encryption. Okay, so this one is yet another interesting application, not as mature. It is in smart grid, smart agriculture communications, I beg your pardon, whereby smart agriculture is now embracing autonomous machinery and robots in the field, crop monitoring, livestock monitoring, as well as crop storage management. So, for example, temperature. And so the passive optical network technology can provide broadband connectivity as well, and more importantly, support mission critical applications. For example, applications that detect changes in livestock health, as well as changes in crop storage conditions, because that could wipe out a single harvest within a few minutes. So that's a very interesting approach for using the PON technology in smart agriculture. All right, so we also must not forget the usage of fiber and PON technology more broadly in mobile networks. And here, what I've done is I've overlaid the standards of PON. No, this is not working really. Oh, so here I have overlaid the standards of PON with the different flavors and different generations of mobile networks here. And as you can see here, over the last 30 years, PON standards have advanced so much so now we have aggregate bit rates of up to 50 gigabits per second. And soon we will see aggregate bit rates of up to 100 and maybe 200 gigabits per second. If we look at the mobile networks, you will see that as we go towards 2030, IMT 2030, so that is actually the blueprint. Everyone considers this to be a blueprint of 6G. We're looking at these use cases here, these applications here. And as you can see here with the high bandwidth, latency sensitive applications, we will probably need very high carrier frequencies, which means, we're left with shorter range, smaller size, and highly dense cell. So for us to reach the length, as well as the capacity that's required, PON technology makes sense. And this makes even more sense from a business point of view when there is already available fiber that's embedded and that's already installed where you want to deploy with 6G. So let's talk about IMT 2030 a little bit. It is a framework for future mobile communication systems beyond 5G. And as I've said, many considers this to be a blueprint of 6G. And here I have the view graph of the usage scenarios of IMT 2030, whereby we have 3 in green that are extensions of 5G and 3 that are completely new. I would like to call out the enhanced mobile broadband here, which is the use case for 5G, which is now extended to immersive communication. This goes back to our original discussion about human to machine and cyber-physical convergence. I would also like to call out the 3 new use cases. The first is ubiquitous connectivity to bridge digital divide of underserved areas and rural areas. AI and comms to support AI applications, as well as integrated sensing and communications to facilitate spatial and environmental info. And so regardless, the 6 use cases must adhere to 4 overarching design principles, being sustainability, connecting the unconnected, so that's a societal benefit, security and reliance, and ubiquitous intelligence. So everything is underpinned with machine learning. Okay, so when it comes to machine learning, this topic is widely explored, and here I'm going to focus on the telecoms network. And shown here is a non-exhaustive list of the breadth of the applications of machine learning over the last 5 years. And although machine learning, seemed to have exploded onto, the telecom scene in the last 5 years, it has been a topic of exploration. And I feel like I'm preaching to the choir here. The computer science community, have been looking at this for the past 70 years. And in fact, the term machine learning was coined in 1959 by Arthur Samuel and defined as a field of study that gives computers the ability to learn without being explicitly programmed. And, the revival that we're seeing now is due to 4 intersecting and dependent variables and factors, which we haven't seen before in previous generations, and that is the availability of data. Now we have big data, we have internet, we have IoT that contributes to massive amounts of data to train and test and validate. We also have access to open software toolkits, very, very advanced hardware that allows us to process and analyze very quickly. Cloud and edge computing have democratized machine learning, and a wider population can experiment with machine learning. And finally, investments are being made into the infrastructure as well as upskilling the people, through institutes, research institutes, industry, as well as governments, and they are actually working together to accelerate the adoption of machine learning. So these 4 intersecting factors are what is actually driving the revival that we're seeing today. Okay, so I'm going to put out a provocation here. The question is, machine learning is great. We've been looking at that for the last 5 years. It's been great for my paper account, great for my citation. But the question is, at what point does it make sense, right? When does machine learning make sense, and is it really practical, especially, and I'm going to provocate this, in the access network segment? So yes, it makes sense when the problem you're trying to solve cannot be represented by a physics-based mathematical model. It makes sense if this model exists, however, to solve it is computationally complex, costly, time-consuming to solve. However, in saying that, there are still key challenges, and these challenges are especially amplified in the access network. The reason is, compared to the core and the metro network, access networks lack data acquisition and monitoring infrastructure. So we have insufficient data to train, validate. It is very cost sensitive because this network is shared by fewer users. So it's not always cost efficient to label data or clean up the data. There is limited computational resources, at most edge computing and not ubiquitous. And it is a very dynamic environment. This is very close to the users. And so any movement in user behavior and the application that they choose to use will affect the efficiency and the accuracy of the learned models. And so these are the characteristics of the access networks that give rise to a host of challenges, 3 of which I am going to discuss today. All right, so the first one is the availability of representative data. Here we have a lack of monitoring infrastructure, as I've said, but it's compounded by the fact that it is cost sensitive to retrieve and label the data. And so these are barriers to actually collecting enough sufficient data for training, testing, and validation. And as we know, limited and biased data sets are models that are, lacking in robustness and generalization capabilities. And so how do we overcome this? You could use, some emerging approaches that I'm going to talk about, one of which is online learning. You can train with, a small sample, and then you deploy the model, and in deployment, you can actually collect more samples to improve the model. So online learning is space and data efficient. It's also time efficient in deployment, and it adapts very quickly to network changes. The next is active learning. It first trains on a very small data set, and then we proactively query an oracle. This could be human, it could be a software and database, to actually selectively select the unlabeled samples to label. And here, active learning is very helpful when you have large volumes of data that is very costly to label, and you want to, select it. You want to be very conscious in how you select unlabeled data to label. Then we have generated adversarial network to synthesize the data from real data. Here we have the framework whereby we have two neural networks. The first one is the generator, as we know, that captures the distribution of the real data. And then we have the discriminator, whereby it decides whether a sample is real or synthesized. So the generator's aim is to generate data so real that the discriminator cannot tell the difference. And the discriminator's aim is to accurately classify real data. And so at the end of the training phase, both neural networks will be optimized such that the generated data is indistinguishable from the actual data. And that's how you get your data from the lack of having sufficient data. And finally, we have transfer learning, whereby parameters of the source model that's trained on a source task is transferred to the target model to actually perform the target task. And so what happens here is the target model can then be refined by a small sample of data set. And then transfer learning is especially helpful when you have a very small sample to start with, and it's very good for rapid adaptation and performance improvement. Let's go on to the second challenge, which is explainability. So we know that machine learning models are black boxes. There's a lack of transparency and understanding of the factors that drive the decisions. And so, although there is improved work efficiencies, network domain experts, network operators need to trust and have confidence in the model outputs. And so this is more important in a dynamic environment such as extended networks, whereby the trustworthiness of the machine learning model in one setting does not automatically translate to another setting when the network shifts. And so here we have seen a growth in explainable AI in telecoms network to enable network engineers and operators to better understand the processes, the underlying factors, and the decisions. And so explainable AI can improve the explanation by giving us meaningful information about how to interpret those results. It also can help improve the interpretation to reveal the type, the extent, and which part of the input data has influence in the output. And an example would be the feature important analysis that we have used, and we use it to gain insights into the input features and the contributions to the model output. I am so sorry, this is just very distracting. All right, so we use XAI here to select our important input features. Why we want to do that? So that we can only use the important, we can discard the less important, so that we can reduce model complexity and training time. And we test this in a human-to-machine comms over access networks. This is how it works. So the human, shown here, will send control signals to remotely control a remote robot to touch and move an object. And then data from the robot sensors will be sent back. So this will be part of the haptic feedback, will be sent back to the human, eliciting touch sensations. Now, because we are looking for real-time immersive communications, this control and haptic feedback control loop has to be within 10 milliseconds. And so because of this constraint, there's a limit to how far you can deploy the human and the machine. So how do we overcome this? We actually place an intelligent edge server in between the human and the machine. And so what it does is actually predicts the touch events, so the control events, so then it can preempt and send back the haptic feedback. And so this way we can truncate the optical loop or the control haptic feedback loop to improve and remove the dependency on the human-machine distance. And so just to remind ourselves, we're going to use XAI to select the important features. We're going to remove the unimportant features to reduce training time. And shown here is the XAI framework. I won't go through it in detail, except to say that for data preparation, we're going to use, or we have used our test bed, whereby we use some three input features, basically data from our haptic gloves as an input to train a machine learning model to detect whether it's going to touch or not touch a particular object. And then we're going to do feature selection, whereby we use global shape explanation or shape XAI technique to rank our input features. We remove the least important feature until we see a degradation in performance. And at the end, so as you can see here, we have high input to low importance input, and we remove these low importance input. And at the end, we end up with 29 features out of 64. And shown here is the impact of removing those unimportant features. As you can see here, the framework that we've used has a lower average training time as well as jitter and a very good performance in terms of detecting touch and no touch events. So finally, if you can bear with me for another 5 minutes, I'm going to talk about the third challenge, which is adaptability to dynamic environments. So the common assumption with machine learning is that data is stationary, it's identically distributed, which means distributions from training and deployment are going to be identical. But this is not true, and we know this is not true for excess net lease, which is highly dynamic, dependent on user behavior. And so when your underlying distribution of the original data that you use for training is not the same as that in deployment, then you give rise, or this gives rise to the concept drift, the phenomenon of concept drift. So there are two types of concept drift. We have got virtual drift, which means changes to the distributions do not affect model accuracy. We then have real concept drift, whereby changes to the distribution, if you're still using the same decision boundary, will lead to inaccurate and poor prediction. And so what we want to do is we want to detect concept drift, and we want to retrain the model as soon as possible. Okay, so here we have an adaptive concept drift and adaptation framework that we're currently working on. And the aim is to detect changes in traffic distributions, and we want to retrain this model as soon as possible. And so in operation and in deployment, the real-time incoming packets are chunked into sliding windows, and the traffic distribution is evaluated and compared to a pre-trained model. Now, any dissimilarity in this distribution will actually give rise to a prediction error. And when this error reaches a warning level, we know that the pre-trained model is actually unstable, and we start shrinking the sliding window to give us a more updated evaluation of the distribution. At the same time, we start collecting the new incoming data so that we can potentially retrain the model with this new data. So once the error reaches the concept drift level, we then commence machine learning training. So we test our framework in a simulated 10 GPON, G passive optical network. We actually collected 6 different human to machine scenarios of varying traffic loads from our experiments. And shown here are 3 different scenarios of punching a ball, of moving an object, and of bouncing a ball. And so again, the aim of the ADA framework is to detect changing scenarios. We want to retrain the model as soon as possible when concept drift is detected. And the whole point of this machine learning model that we are training is that it needs to predict bandwidth that is required by each of these scenarios, and so that we can pre-allocate this bandwidth to minimize uplink latency. So shown here is the uplink latency performance. It's a preliminary results that we have, and we're doing more work here. And here, as you can see, every 1 millisecond, we're actually changing the scenario, and we're actually changing the traffic load. And, we compare ADA here in orange to the baseline, to machine learning with bandwidth prediction, machine learning with concept drift detection. As you can see here, the network that uses the machine learning with the ADA framework rapidly detects changes in scenarios as well as traffic loads, but it always yields a very stable, it's not actually, oscillating, very stable uplink latency. All right, so what are the next steps? We've talked about robustness, dynamicity, and interpretability at length. There's still a few others that I'd like to call out. This is security and reliability. So machine learning is not, sort of Teflon against vulnerability. So we have got to look at, how do we deal with data poisoning, transfer learning attacks, especially at the access networks that are so close to the users. We want to talk about energy efficiency, and I know our invited speaker, Karen, will be talking a little bit about this. We want to look at computationally efficient machine learning models and energy efficient hardware. Then, when you go into deployment, there's always going to be a trade-off between processing time, between the cost and model accuracy. So we need to really manage the risks when we actually look at these trade-offs. Here are some standardization activities. What I want to say is that, all SDOs are looking at integrating machine learning. At the moment, it's only at the network automation level, but the consensus is they will work together so that there is one interoperable global set of standards. And I'll end with this slide where I started. I'd like to say that, we're really blessed to be working in this era of, human robot collaboration and, experience-oriented communications. I truly believe that, this types of, cyber-physical convergence and communications can really remove a lot of inequitability in how people interact, socialize, work, and play, as well as learn. And so with that, thank you very much for listening to me and for bearing with me with the tech issues. I'd like to acknowledge some past and present students, postdocs, as well as collaborators. Thank you very much.
We have time for just one quick question. While they're setting up, I just have one question about the ML models for access networks. For a lot of times in access networks, we're looking for outliers or corner cases. How do the models handle those?
Yeah, so in the particular models that we've been looking at, is actually service realization.
Okay.
So we're looking at a human, so we're looking at how we detect what's coming in, and I'm going to preempt what I can send out.
Got it.
So, but anomaly detection for protection is also very much a hot topic, as you have seen from the list that I'm on. Yes.
Okay. So one more question. Yeah.
So, you talked about the ponds of interest for radio networks, right? So, but your applications here didn't include the radio part of it.
Yes, yes.
Do you think that's going to play an important role here, and what are the issues about it?
Yeah, so we've done some work in the past where we looked at transfer, where we have different, sort of cells and different antennas. And what we've done is, and the limitation to that was it was a heterogeneous type, homogeneous type of deployment, whereby the transfer learning is used to transfer a known model, the parameters of a known model, to another antenna segment that has similar application and similar traffic. The benefit of that is you can actually ramp up the deployment very quickly because you transfer those parameters. But the limitation is that if you deviate from the types of traffic and the types of behavior, then transfer learning will not be efficient. So we have looked at that in the fiber radio.
And do you need cooperation between the PON and the radio network?
Yes, correct. Yeah. So cooperative deviating is what we looked at. Yeah. And we use transfer learning to detect and predict the bandwidth that's required in each segment. So, yeah.
And is it recorded or is it going to be live?
It's recorded.
Okay.
Yeah.
So, rather you create online, this is back.
So I'll just introduce and we'll start the video and then